So we again already know kind of some of the theories behind or some of the definitions and terminology we're using in solving higher order differential equations. We know we've also learned how to solve a second order differential equation when we know one solution. So we're doing reduction of order. Now let's actually look at how do we find those solutions. So we're going to look at homogeneous linear equations with constant coefficients for right now. And so let's consider a times y prime plus b times y equals 0. And what we mean by constant coefficients is a and b are not functions of x, they're just constants. And so y prime is equal to minus b over a times y. And let's go ahead and look at this. If I got this is actually separable. I can actually separate it out. When I separate this out, I will get y is equal to e to the mx. So I happen to know that this is the solution to this is y is equal to e to the mx. I've seen that before. So y prime is m e to the minus mx. You can then plug that in. So I happen to know this is a solution. Again, you can prove this is by doing separation of variables because it's a separable equation, and you'd find the solution. Since I know this is a solution, I can find its derivative, I can plug it in. And when I do that, I get am e to the mx, when I plug it into my derivative, my differential equation, plus b e to the mx. And I notice that each term has an e to the mx in it. So I can pull that out. So I get e to the mx times am plus b equals 0. So am plus b equals 0 because e to the mx can never equal 0. So it tells me my m is equal to minus b over a. So all I did was solve this nice little linear equation, basically. So this is actually, then we can use this. Now we're going to consider a times y double prime plus b times y prime plus c times y equals 0. Let's go ahead and just suppose for a moment that y1 equals e to the mx. And so let's just consider that that could be a solution. Let's guess that that is a solution to this. So we're going to plug it in. That means we're going to prove it is really a solution. So we're going to do y prime and y double prime. So y prime would be m e to the mx. Y double prime would be m squared e to the mx. So we get a m squared e to the mx plus b m e to the mx plus c e to the mx. And I notice that all of these have an e to the mx in it. So I can pull that out and I get a m squared plus bm plus c equals 0. E to the mx can't be 0, so that must mean a mx squared plus bm plus c equals 0. This is known as our auxiliary equation. This is just a quadratic equation. You know how to solve quadratic equations. Remember, quadratic equations could have two real solutions. So we can have two distinct real roots. It could have one distinct real root, or it could have two complex conjugates as the roots. So this is just a quadratic equation. We've been solving this for a long time. So let's see what we can do. Let's look at the case of this. There's two distinct real roots. We'll call them M1 and M2. Then what we have is, remember, we assumed back here that y1 is e to the mx. We assumed that that was my solution. So that means that y1 is e to the m1x. But there are two m's, so that must mean the other one must be y2 equals e to the m2x. And therefore, my function is y is equal to c1 e to the m1x plus c2 e to the m2x. And that's it. That's my solution to that differential equation if we have two distinct real roots. If you have two distinct real roots, the solution is really easy. You're just going to solve that auxiliary equation and come over your solution here. Let's look at case 2, where we have one distinct real root. We'll call it m1, which means we have y1 equals e to the m1x. However, a first order differential equation has one solution. A second order differential equation should have two solutions. A third order differential equation should have three solutions. So this should have two solutions. I only have one. But I could find y2 using reduction of order. So I could do that same thing we just did of finding reduction of order, of finding y2 when we know what y1 is. And when I do that, I end up with y2 is equal to x e to the m1x. I'm not going to go ahead and do that, but you can go and see how to do reduction of order and prove that that's the case. So that means we now can say that our y is equal to c1 times e to the m1x plus c2x e to the m1x. And so there's your solution here. That will be what it always will be. Okay. Let's look at case 3, where m1 and m2 are complex conjugates. What that means is m1 is, let's say, alpha plus I beta. M2 would be alpha minus I beta, because that's what conjugates are. So we can then put that in, y is equal to c1 e to the alpha plus I beta x, and plus c2 e to the alpha minus I beta x. So there's my solutions as before. But this isn't very pretty, and mathematicians like things that are pretty. This isn't very elegant as my solution. So let's just see what we can do with this. One thing is e to the alpha plus I beta x could be e to the alpha x times e to the I beta x. Same thing with the other one. We can put those and separate them into two different a's. Then I notice that each one has an e to the alpha x, so let's pull that out. So I get e to the alpha x times c1 e to the I beta x plus c2 e to the minus I beta x. Well, okay, so we got that. But I don't like this. I don't like this e to the I beta x. I don't like that. I would like to find a way to simplify this. And I can do that. And this is known as Euler's formula. Euler was a pretty famous mathematician. He did an awful lot of work. He was a Russian. He did an awful lot of work in mathematics. He's had his fingers in many different branches of mathematics. And this is known as Euler's formula. By the way, E is named for Euler, supposedly. That's the rumor is, the urban legend. And what Euler's formula says is that e to the I beta is equal to cosine theta plus I sine theta. This is like one of the most versatile formulas in mathematics. We love this formula in mathematics because it really makes life much easier to work with. So this formula we're going to now use to simplify e to the I beta x, which would be cosine of beta x plus I sine of beta x. And e to the minus I beta x, it'd be cosine of minus beta x plus I sine of minus beta x. Remember that sine is an odd function. So the sine of minus beta x is minus the sine of beta x. The cosine is an even function. So the cosine of minus beta x is just the same as the cosine of beta x. And so we now have y is times e to the alpha x. Remember, we pulled that out. And then we have this c1 cosine of beta x plus I sine of beta x plus c2 cosine of beta x minus I sine of beta x. So now let's try to get terms together. Let's bring all the cosine of beta x terms together. That would be a c1 plus c2 times the cosine of beta x. Let's take all the c1, the I sine of beta x's together. But I is just a number. I know you don't think it is. It looks like a letter, but it really is just a number. So I could actually pull that I out, and I get c1i minus c2i sine of beta x. So when I'm going to pull that sine of beta x out, I've got a c1 times I and a c2 times I. But those are just numbers. So instead of calling them c1 plus c2, that's just a constant. We can just call it anything. I'm going to call it c1 just for lack of something to call it. And c1i minus c2i is just a constant because I is just a constant. I is the square root of -1. So we got c1 times the square root of -1 minus c2 times the square root of -1. That's just a constant. Let's call it c2 and you can call it anything you want. You can call them A, B, I don't care what you call them. But we now have that our solution, when we have just two complex conjugate solutions, is going to be e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. Notice there's no I left in this. And it's mostly just using whichever one you happen to have when you go to solve these. So let's go ahead and solve this differential equation, y double prime minus 3y prime plus 2y. I'm going to first find the auxiliary equation. And I don't need to actually go through and let y equal. Remember, we're letting y equal e to the mx. We don't need to actually do that and find out what that is. We don't need to plug that in because it will turn out this will always become m squared minus 3m plus 2 equals 0. It always will come out this way. Notice this is y double prime and it's m squared. This is y prime and it's just m, and then it's just plus 2. There's no, this is no derivative, so there would be no m here. And it always works out this way. You can actually prove it to yourself if you want to. Plug it in, see what happens. You will get this. So all we have to do is solve this quadratic equation, and it just means factoring or using the quadratic formula. In this case, this is a really nice, easy factor. So I'm going to factor this, and we get m equals 2 and m equals 1. We get two distinct real roots. So therefore, my solution is y is equal to c1 e to the 2x plus c2 e to the x. And that's it. There's your solution. Way simpler than doing anything else we've done. Again, the reason we're doing this is because y equals e to the mx. We're then finding those m's. And we just did. Let's do another one. So again, I'm going to first find the auxiliary equation. So if I have y double prime, that gets replaced with an m squared. Y prime gets replaced with m. And then we get 4. So we get m squared plus 4m plus 4. That is your auxiliary equation. Again, you want to solve this. This factors as m plus 2 quantity squared. So m equals -2. So we get one repeated root. Instead of two distinct roots, we get the case 2. So case 2 says our solution is, remember, we are using the fact that y equals e to the mx, and you're just trying to find what that m is. We found that m. It'll be c1 e to the -2x, but I can't do the other one as just being plus c2 e to the -2x, because if I did that, these are not linearly independent. This is where the whole idea of linearly independent is very important. It reminds you that you can't just write this as e to the -2x by itself. This is where that x came into play. And again, we found that using reduction of order. So we could do the reduction of order and find that. Okay, so there's your solution to that one. Again, you can prove it's a solution by plugging it in. If you have initial conditions, you can find out what C1 and C2 are. If you have boundary conditions, you can find out what C1 and C2 are, and so forth. Let's try one more. Let's try 2y double prime plus 2y prime plus y equals 0. So again, get your auxiliary equation first. That'll be 2m squared plus 2m plus 1 equals 0. Again, we are using the fact that y is equal to e to the mx, and we're trying to find those m's. So we're using that fact, we're plugging that in, and we'll always get this auxiliary equation when we're done. And then you just have to solve this. Well, this turns out to be m is equal to -1/2 plus or minus 1/2 I. So you can use the quadratic formula, you can use technology. I don't care how you find this. Your calculus will do this. Wolfram Alpha will do this. Lots of different ways we'll find this solution for you. Just find that solution. You can do it with the quadratic formula for all I care. Since this is complex conjugates, y is going to be e to the alpha x. Alpha is the real part of this complex conjugate. So the real part is -1/2 x times C1, the cosine of beta. Beta is the imaginary part of this. So my beta is 1/2 x plus C2 sine of that 1/2 x. And there's your solution to that one. And that's all there is to this. And it's kind of a memorization of which form it is. If you want to derive it each time, we derive them all. You can do that, and that's fine. Let's do just one more. This will be an initial value problem. So this means that I'm going to go ahead and find out what the C1 and C2 are in the end. I know I have C1 and C2 because it's a second order. And so I get my auxiliary function first is m squared plus 1 equals 0. So that's my m is equal to plus or minus I. So I know I have complex conjugates. In this case, the real part is 0. So think of it as your alpha is 0, your beta is 1. So I've got, again, y equals e to the alpha times x. So e to the 0x times c1 cosine of beta x, so 1x, plus c2 sine of beta x, so 1x. E to the 0x is, of course, just 1. So we actually have that y is equal to c1 cosine of x plus c2 sine x. And now we can go ahead and find our constants by plugging in the initial conditions. Our initial condition was we need to know what y prime is to do the initial conditions. So let's find y prime. That'll be minus c1 sine x plus c2 cosine x. And we had y of pi thirds. That'll be c1 times the cosine of pi thirds, and the cosine of pi thirds is the 1/2. So 1/2 c1 plus c2 times the sine of pi thirds. The sine of pi thirds is square root of 3/2 times c2, and that's going to equal 0. And then y prime of pi thirds is minus c1 times the sine of square root of 3/2. I'm sorry, pi thirds, which is square root of 3/2 times c1. And the cosine of pi thirds is 1/2. So 1/2 c2, and that's going to equal 2. So you want to solve this equation, this system of equations, c1, 1/2 c1 plus the square root of 3/2 c2 equals 0, and minus the square root of 3/2 c1 plus 1/2 c2 equals 2. Solve that, and you get that c1 is minus the square root of 3, and c2 equals 1. So I get y is equal to minus the square root of 3 times the cosine of theta plus the sine of theta. And there's your solution. One thing I want to just kind of mention is in general, this was an equation where we just had y double prime plus y equals 0. If you have that formula of y double prime plus some constant times y equals 0, or y double prime minus that constant times y equals 0, I want to talk about what the solutions always will look like. You can actually solve this. When you solve this, you will get complex conjugates, and you will always get c1 times the cosine of the square root of k times x. I'm sorry, I already did the square root of k squared, so it's just a k times x. So I used the k squared. Plus c2 sine of kx. If I were to solve this one actually will give you 2 real roots, because you're going to get m is equal to k squared, m squared is equal to k squared, so m is equal to plus or minus k. That will give you y equals e to the k, k1x plus y2, c2 e to the minus k, k2x, I shouldn't say minus, but you'll get those two answers. Actually, I guess you will. You get k minus k. And it turns out that you always will get, so you get y equals c1 e to the kx plus c2 e to the minus kx. And you're always going to get that with these answers. This will always give you complex conjugates. This one will always give you two real solutions. This is where we actually can use the hyperbolic cosine, hyperbolic sine. And if you did a little bit of work with this, you would get that e to the kx, c1 e to the kx plus c2 e to the minus kx. You can actually do a lot of little algebra on this, and this actually becomes c1. And again, that's c's different c, but just c1, the hyperbolic cosine of x, plus c2, the hyperbolic sine of kx. And this is where we like these, is because it takes your e to a bunch of powers and makes it into basically cosine and sine kind of idea. All right, so that's how we solve second order differential equation with constant coefficients.